And this, there, all right. So it'll be a recording. So there are a series of puzzles to solve, and I will demonstrate them. And if you don't have a computer at all, make a friend with somebody and share with them, because you won't have any fun if you aren't solving the puzzles. So you should get some kind of virtual machine running, which is the only difficult part of the workshop. You get a VMware machine running. Hopefully a lot of people can do that, and if not, we can help you. I have VMware and VirtualBox images, and you have to unzip it with 7-zip or with Dion Archiver on Mac. So if you are not able to do the projects, raise your hand and get attention. Don't sit there miserable. Anyway, let me show you what's going to happen. Here's the setup, explaining how to do it and where to download virtual machine software if you don't have it. And I even have some cloud instances. If you have some machine that can't run VMware at all, like an iPad, you can possibly get some of this done by using a remote cloud machine, but it'll be kind of inconvenient. But if people get very frustrated with VMware, I can try setting you up with that. Anyway, then you get down to these challenges. So I'll demonstrate these, but let me just start with some general remarks. I thought that analyzing malware was impossible years ago, because I thought the only way to do it was to run something like IDA Pro and get 10,000 lines of assembly code, and only super elite people that could read that stuff could analyze malware. And that, of course, was the first way to do it. And that kept it out of the hands of most ordinary people, and only the real experts in assembly language could do it. But what happened 6 or 7 years ago is practical techniques started to appear. And I learned it first from a European anti-malware group that came rarely to the United States. And they had a class in San Jose, and they taught us the European way to analyze malware, which was very nice. And they were sort of horrified. They would bring in one of the most powerful and simple techniques is you run the malware in a virtual machine, deliberately infect it. And then you run monitoring tools on the compromised operating system and see what they tell you and believe it. And I'm like, what? That's just asking for it. And they say, yeah, that is sleazy. Smart malware will fool your tools, but some of the malware is stupid. So you try using just the simplest technique. And you have so two important lessons that were hard for me to get about malware analysis. The first one is you can't trust anything. Your tools, you can't trust them. You can't assume that your operating system is going to work. You can't assume that any part of it works the way it should. Very frequently, you launch a tool and it doesn't work, because the bad guys are smart and they put in some kind of countermeasure for that tool. So you just have to have a pile of tools and try another. The next thing is you have to forget about really understanding it in any depth. You could make a PhD thesis out of analyzing malware, but most of us are not trying to get a PhD thesis. What we want is to answer a few simple questions. So before you start, be aware that you're going to be constantly confronted with baffling complexity and far too much information. The job is not to find more information. The job is to somehow remove 99% of it to give me the information I care about, because normally all you care about is, how do I tell if a box is infected? What exact harm did it do? How do I get rid of it? And how do I block it on the network? That's all I want. I don't really need to know every detail about how it works. So anyway, so that's the general philosophy, and I found this very difficult. I came from a physics and mathematics background, and what I had learned is when you are reading a book, you read a sentence and you never proceed to the next sentence until you completely understand this sentence. And I really hated authors that will say something and then say, to explain. And I say, you idiot. I just spent an hour trying to figure it out because I assume this is knowledge in linear order. And you have to forget that entirely. I had to develop a skill, which I think managers have, which is to skim through something, ignoring all the blah, blah, getting the high points to decide whether I care enough to look at more. That's how you deal with too much information. So what you got is you got little puzzles here. They pretty much all come from this book. This book made it possible for me to teach this class. There's Dylan. Good. He's also an assistant. So Dylan and Stuart are both there to help you if you have trouble. Anyway, this book comes not only with a whole bunch of useful instructions how to analyze malware, it also comes with a bunch of harmless malware samples. They're not entirely harmless. They don't spread and infect other boxes, but they do sort of foul up the machine. So I really wouldn't recommend running it on a machine you love. But you're not going to infect other people or anything, but they are going to kind of foul up the machine, and some of them are kind of hard to remove once you put them on. So that's why you typically put it on a virtual machine, and I just provided a Windows 2008 virtual machine because it's the most recent version of Windows I can run without a product key. When you start it, it will say you have no product key and you have to wait 15 seconds to say register later. And you can use it without a product key, which is what we're doing. All right. So if you have not done anything like this before, you can still do the easier parts of this workshop, and that's what I learned. Malware analysis is no longer impossibly complicated and difficult. Quite a few parts of it are fairly easy, like running a monitoring tool and deliberately infecting a box. Basic dynamic analysis is quite achievable, and that's what you get from automated sandboxes. So once you have a virtual machine going, there are challenges here, and there's a scoreboard. You earn points just sort of to keep people interested. So there's 4 general categories. Basic static analysis is figuring out, without running the malware, what it is. This is like when you have Christmas, you get a package, and without opening the package, you try to shake it and feel it and figure out what's inside there. Very superficial, not very accurate, but very easy. And this may be enough. You do things like send it up to VirusTotal. Maybe somebody else already figured out everything about this malware. In that case, you don't have to. Basic dynamic analysis is the process I described, where you deliberately infect a virtual machine and let the malware do stuff, and then you watch to see what files does it create, what registry keys does it create, what network traffic does it generate. And if the malware is not too complicated, it will not be designed by a crook who planned for that. So it will not kill your monitoring tools, which it certainly could. But if it doesn't, then you get the results that way, and that was easy. If those things don't work, then you have advanced versions of it. Advanced static analysis is the one that scared me off, where you actually run this thing through a disassembler and get line after line of assembly code and read it and try to figure out what it means. And that is possible, although it takes a lot of training and practice, but it's very burdensome. So you use the simpler techniques to help you focus on the part that's important, and you do static analysis on just that part. And then there's advanced dynamic analysis, where you run the malware in a debugger and manipulate the way it runs, stop it at breakpoints, and change values to make it go to other parts of the code and so on. This is quite useful and not that hard, but you have to get used to debugging. So we'll play a little bit with that. Those are the general categories of malware analysis, and some of them are easy and some get harder. The other thing I should probably mention is I learned that 90% of malware analysis is Windows software development. What you're really learning is how Windows works, because all the malware is simply abusing normal Windows features. And the more you study this, the more I discover something that I think Microsoft knew all along, which is software developers use the parts of Windows they are not supposed to use all the time. Microsoft has their official API you're supposed to use, and there's a whole bunch of supposedly secret, undocumented things that people use all the time. And the malware designers learn more and more of those obscure ways to do things backwards, so it will be harder to figure out. So let's play with some basic techniques. In challenge 1 here, you've got some samples. So the first thing you could do is you could send it up to VirusTotal. I don't think I will. VirusTotal is Google's service. This just runs it against antivirus engines. And if it's already recognized, you'll find it. The ones in this book are probably up there too, but they're not terribly malicious. So when I ran this one up and was analyzed, I knew it was only getting 2 out of 13 hits. But then we can start using tools to let you see inside it. So the first one is PEView. There's about a dozen tools we use here, and they're all pre-installed on this virtual machine. If you want to make your own machine, there's a link at the bottom to all the tools. Or, oops, I think I forgot, I accidentally moved it from my page, but I can add it later. Anyway, the tools are all freely available, but they're all installed on this virtual machine. So the first one is PEID. Windows executable files are PE files. They are portable executable files. That is the format of all Microsoft executables. And this PEID is a tool that helps you find out what's in a file. So I'm going to open my malware samples right on the desktop here. I want to open, let me get my instructions and move my screen around. Okay, I want to start with Lab 101, okay? So I open this thing here, and I go to my desktop, malware, binary, chapter 1, Lab 101. By the way, Windows files typically have executable files and libraries, DIL files. This is one of the many things that's brilliant and stupid about Windows. They reuse software, they reuse library files among many executables, which makes things load faster and consume less memory, but it is horribly unsanitary, and almost many attacks, I think most of them, involve running malware by tricking it into loading the wrong DIL. Because since you can just request a library function during runtime and it will load it, it's easy to just tell it to load the wrong library and it will just do it. So anyway, we're going to look at the exe here, and this will show me the entry point. It'll show me here, this is one of the most useful things, what language it's written in. So this was written in Visual C++ and compiled like most things. So it's very simple. And let's see what else I want to find on that one. All right, that's PEID gives me just general information about it, which I've got down here. And it shows me the first few bytes of the files and the language it was written in. So that's one good thing. And if you look at, say, a Kaspersky report about malware, they often tell you the compile date. And we're going to see that in the next tool, PEView. PEView gives you a more detailed look at how malware is constructed, or any Windows executable. These things are not specifically for malware. Developers use these tools too, just to find out what's going on with their own software. So that's chapter 1 I want to be in. Come on, chapter 1. And I want to see an exe, not a DIL. And there's labo101.exe. All right, so this is showing me the structure of this portable executable file. At first, it's got this MZ header, like all Windows executables do. That is the header to indicate it's executable, and this ancient DOS header here. And then it has sections. Every PE file has certain sections. The text section contains the executable instructions. And then there's data and resources and things like that. This one just has text, R data, and data. Some of them have more. And so if you go to the text, this is executable code, which doesn't look like anything other than random bits in this viewer. And you can see some information about when it was compiled by going to the image file header. So that is in here in the NT headers. Okay. And there's a signature. And there's an image file header. And here's what I was talking about earlier that Kaspersky uses a lot. This is where you find out when it was compiled. This turns out to be useful in 2 ways. It's useful for attribution. You can find out what time of day it was when it was compiled. And if you get a lot of samples, you can see if it's during business hours in a time zone. And you can also tell if 2 files are related because they'll both be compiled within a few seconds of each other because they're part of the same thing. So that's often helpful, although of course this information can be falsified, and there are some software products that always fill this with junk data instead of it being accurate. But you've got that information there. And then there's bin text. This is probably one of the more wonderful first steps. If you do this on Linux, the first 2 things you do with the command file, and this you do with the command strings. The first thing is just to assign the readable text in a file, and the strings command has been ported to Windows and you can use it, but it's worthless because of Microsoft. Microsoft is an international operating system. It supports foreign languages like Arabic and Japanese and stuff, so 8 bits are not long enough for a character, so almost all the strings are in Unicode, and the traditional strings tool will not find them. So instead, you use this tool called bin text. This is very useful, and it also introduces you to the sloppy form of thinking that you have to adapt to. So bin text is installed here. This is a Windows graphical tool that finds strings. And I want to open, I think, that same file. Let's start with that. Browse to chapter 1, lab1.exe, and go. Now, what this tool does is something very simple. The file is just a series of bytes. And this tool just goes through the bytes and defines if there's a series of bytes longer than a certain minimum length, like 4 or 5, that is readable. And if it is, then it calls that a string and prints it. That's all it does. So sometimes you see meaningful things, like here's this program cannot be run in DOS code. These are Windows API calls, which are very easy to read. They all have this Visual Basic convention of using capital letters at the start of each word. They often end with an A or an EX or a W, the A for ASCII output, the W for wide output Unicode, the EX for an extended version, and so on. And you can just tell what they do. So by just looking at the strings, you can start guessing what the malware does. And I'm not seeing as much junk as I often see. Usually the code section, the text section, creates a lot of junky strings, but this tool may be preventing it. There's one, warning this will destroy your machine. That's not quite clear why the malware author wanted to scare you with that. But anyway, what you're doing is looking at the strings, and now you are invited to guess what the malware does. This does not prove what it does, and it would be easy to fool you, but most of the time, for simple malware, you can just tell what it does just from the strings. So this malware apparently does something with a file. It has some API calls using file like find first file and find next file and create file. So apparently it hunts through the file system for something and then creates something. If it doesn't find it, then it calls some dills, kernel32 and msvcrt.dil to get API calls, and then it calls kernel32.dil, and this is another good clue. It's got kern-e132 and kernel32. This is something malware authors love to do. They name their malware something that looks very close to a normal Windows system file, so that if you find that file on the disk or that process in the running table, you will think it's harmless. So that's a pretty strong indication that this creates something malicious called kern-e132. And here's a path leading that kern-e132, telling you where it's going to go. See Windows System 32, kern-e132. And here's more about closing files and such down here. And down at the bottom, I've got string compare. These are the specific functions it uses. Here's a string comparison. So I can already make a pretty good guess that this thing is going to scan through your file system, look for this file called kern-e132, create it if it's not there. This is also another fun fact about malware. People usually get infected many times, right? Because you get trick someone into downloading a file, they might run it a second time because it seems to have crashed and not worked the first time. They might get another copy of that email later. So one issue for malware developers is the first thing you have to say is, did I already infect this box? If so, let's not waste time trying to infect it again. So they typically begin with some kind of search for a clue. And that's very useful to us because we're looking for indicators of compromise that we can use to tell if machines are infected. And typically every machine has a certain file name that's created or a certain mutex, which is a operating system mark that can be seen by all the processes, just a label. Anyway, so that's the joy of bintext, which is very easy to use, very easy to understand, and should be one of your first operations to understand malware. And you find those things. And the next thing I want to show you is Dependency Walker. This one is a little bit more confusing at first. It's a real developer tool. You may remember when you launch Windows programs, you get MSVCR7432 is missing DIL. This DIL is lost, especially in Windows 98, but I'm still seeing it in modern versions of Windows. It is very common that this dynamic linking process fails and the libraries can't be found, and this tool is designed to help you fix that. So I'm going to open the same tool, the same piece of malware in Dependency Walker. There it is. This lets you walk through all the files your software depends upon so you can see if you can find out why it's not working. So there's my file loaded. Let me arrange myself to zoom in better. Okay, so this is a strange piece of malware. Most real software uses many libraries. This uses only two libraries, kernel32 and mscvrt. And if you click on these, you can see not only the library, but you can see exactly which functions were used. And this, by the way, is not guessing from strings. This is actually understanding the code, analyzing it, and see what's called. So this is very good. So it calls, and again, Microsoft API calls are not malicious. They are intended to be comprehensible, so they have nice friendly names that are not too hard to understand, like close handle, copy file, create file, and so on. So you can see all the functions it uses here. You do not see the arguments, and you don't know what order it uses them in, but still, it gives you a lot of useful information. And all right, and here I wanted to point out what we saw in strings earlier. You can find that string comparison call showing you that it hunts through the file system looking for some string to see if it can find it. All right, and kernel32 has the find first file and find next file, so that's what it does to do a directory and hunt through it for things. And if you go down here with the DIL file, lab0101.dil, we can see what networking looks like. So let's open that one. Lab0101.dil is down at the bottom of my list. All right. And this one is the library file. And it has, let me see, I can zoom in a bit. Not working for me. All right, just a minute. There we go. All right. I've got to click here and then zoom in. Okay, so I've got more DILs in this one, and kernel 32, WS3, and MSC VRT. Now I think it's WS2 32 that's got the networking stuff. Let me go back to my instructions. It is. Okay, so I should be able to find these functions in the base of that library. There, okay. So here's the functions that are called: accept, bind, get peer name, connect, and if you do any programming at the socket level with Berkeley sockets in Python or anything, you get used to these methods. Bind is what connects to a port to listen. Accept is what takes incoming traffic. So apparently this malware launches a listening service. And connect is what connects to another one. This does DNS resolution, get peer name. So obviously this malware does networking. It's calling out to some command and control center, receiving something back, which is common, but not all malware does that. So this again gives you quite a lot of information about the functionality without you really having to understand it too well. So if you do that stuff, you can find a couple of things here to get points on the board to show that you've done it, which helps me know where people are. And I think I'll show you one more demonstration here, and then I'm going to stop for a while and we'll go around and just help people. If you're stuck, don't suffer in silence. We're here to help you. Even if you've never done anything like this before, you can do the first few of these challenges anyway. So here's another sample. If you get lab0102.exe, the next one, here you see another very common trick, which is packing. So if you examine the strings in here, you find almost nothing, just junk. So whatever this file is, the strings have been hidden. This is very common. As you know, you can make self-extracting unzip files, like the 7-zip file you have here. So the actual file is compressed. Malware authors very frequently pack the file, not so much to make it smaller, but to make it hard to analyze. So you pack it with some kind of packer, so you can't see any of the strings or code inside the malware. All you can see is the strings or code in the little unpacker file on top. And so that's what you're seeing. If you open that one with PEID, this one is friendly enough to give you a clue. They used a common open source packer called UPX. And UPX, by default, names the sections, things like UPX1, UPX2, UPX3. So if you've got a relatively lame malware developer, but they're smart enough to know not to just give you the naked executable, they pack it with a standard packer that leaves trails. And remember, this is always the case in all security. There are weak attackers and stronger attackers, and you know, you can only fight off the ones at a certain level. The other ones are too hard for you, so this takes us one step further at getting the next step up of attacker. If you examine the thing with PEView, you'll see these sections, UPX0, UPX1, UPX2, that were created by the packer. Since this is a common known packer, you can just download it, install it, and run it. And it's on your machine. It's a command line tool, so you can use UPX to unpack the file. And when you do, it will create another file called lab0102 unpacked. So the original file was 3 kilobytes, the unpacked file is 16 kilobytes. Here's another fun fact: malware tends to be very small because they're sneaking in on network connections and such, so it's practical to read a lot of it. Anyway, so when it's unpacked, now you get Microsoft Visual C++ here. So that takes it back into a readable form, and now you can look at the imports here. And the one thing I should mention now is the functions here have imports and exports. Imports are what normal executables have, which means I use some library code. So if I want to use the socket to open to connect method to connect to a socket, I have to import the DIL that contains it, and then I have to import a handle to that process, the connect method, so I can call the connect method. So normal executables have a lot of imports. They don't typically have any exports because it is an executable. It is not a service provider. It's a service consumer. Library files have a lot of exports, and that's what you see here. The WinINet library, which, as you would imagine, does internetwork, has only a couple of imports but a lot of exports. It offers a lot of services to any executable that wants to use it. That's what exports are. Anyway, and we talked about these. You can go to strings now, and you'll see things like Internet Open URL, and you'll see the domain name of the command and control server. And that's it for that one. So let me just take a look at my start. I think normally stopping at this point is good. Yeah, so do some of these. And I'm just going to go around and help people for a while until I see some of you get on the board. Let's see if people are already on the board. Oh, there we are. A few people are racing right ahead. Oh, yes, and of course, if you're good at this, zip ahead. Don't wait for me. Don't be held back. If you finish them all, there's some more ones like this at the bottom you can click to get to. What's up? Oh, I don't know. Let me figure it out. It's something like that. Let me try and figure that out. Hit here. Oh, good. I actually named it something I can find. Okay. That doesn't sound right. I thought it's like student 1, student 2 or something. Let me see. Let me see if it's gonna work. I probably have more notes. Let me see. Use Safari, Firefox or Safari, not Chrome. Okay, let me try it here. And after I get one, I think it's student 1 and password or something like that. Let me see. Okay. No, just, all right, here, I'll know in a minute. Student 1 and password. Yeah, it's student 1 and password, just plain password. And this is the URL. I'm not sure where to put this. I can put it on my news links. I think I'll do that. I do? Is it still there? It is. Oh, good. And it works. Oh, good. Now, let's see if this works. It looks different. It is. It's student number and password. There's 10 of them. So what? Oh, all right. Then, all right, just a moment. I've got these somewhere. All right, let me try and find them. Is there some other file here? That's bugs, blast. There's an Excel spreadsheet somewhere. It should be 126, really. 126. Lab. NetLab accounts. Oh, that looks like the right file, maybe. Password 123. There's my top security accounts. There they are. Student with 1 digit. Let's see if that works. Understand student 0, password 123. That's it. High security. Okay, good. Those are for people who could not run the VMware at all. Dylan's setting up. You can remote control a machine. They have 10 of those available. Hopefully that's enough. Okay. Anybody else in trouble? Otherwise, I'll just wander around. If anybody doesn't have the VM up, let's try and solve that quickly, because I have no fun now. You're trying directly from USB. Yeah, copy the hard drive first, and then extract. That's one. USB speed. Yeah. That's why copy to the machine first. We can make that. That's fine. Okay.
I think it was password 123.
It looks like they turned off the pods down in Korea.
Uh-oh.
That's bad.
We're looking for that list again, too.
Yeah, but
They're logged in, but the pods aren't there.
Well, apparently the pods are not. So I guess we're hosed as far as the cloud machines. If they've turned it off at Cabrillo, that's nothing I can solve quickly. Student 7, password 123. I didn't know they turned them off. I have no reservations. ULab reservation. Server pod. There are no pods. How rude. That's a client pod. That's not the right one. Yeah, there's no. Yeah, let's see host pod, server pod. What does this thing do? I don't know what that says. CTF, Facebook CTF. It looks to me like they've nuked our pods. All right, sorry guys. Cloud machines have been removed. I need to contact my people at Cabrillo. So you got to run them locally. Hopefully we find enough power.
Is that what you want?
Yeah. All right. Good. I should have paused this recording. This recording is going to frustrate people, but that's life. Trying to find some way to record these things, and this is relatively good at not fouling up the class. Anyway, So I see a lot of people on the scoreboard. Oh yeah, more than 20, good. So that means they've got their VM working and they've solved the first challenge or two and maybe more. So let me finish up the static analysis section, which is gonna be here. Okay, so there's two more challenges here in static analysis and they're pretty simple. I don't suppose I need to do them live so we can get to dynamic analysis. So here, you're just gonna find the packer name. There's a different packer used in this one. So you'll just have to use the same tools you used before. The only point of these is to practice with less instructions. And here you find the date stamp showing when it's compiled using the same thing. So those should go to using the same techniques you used in 1 and 2. So let's talk about dynamic analysis. This is the most fun part usually. All right, so when you have a file and you're going to do dynamic analysis, first you do basic static analysis. That's always your first step to get oriented and to try to make a plan, to find out what you're dealing with. So you use things like PEView and strings or bin text to see what's going on. So we've got this file, lab03.exe. It imports something here. The only DIL imported is kernel 32, and the only function imported is exit process. So this malware seems to do almost nothing. Then if you use strings, you see a lot of readable strings. These long paths of file names like current version run. Now this is definitely the stuff malware does, and you can already guess a few things here. It creates a file called winvmx32, which is again, one of those files that's got a name that will look like it's a video driver or something to make it look harmless. vmfx3264.exe. It connects to a website here. It puts something in the run key. This is how malware attains persistence. You want the malware to relaunch every time the box is rebooted. So as you know, there's things called auto start extensibility points. There are like 40 ways to make things automatically launch in Windows. It's crazy. But one of the very common ones is the registry run key. This is one of the many things that will happen during boot up. So that's putting something in the run key is a common way to make persistence. So that gives you some clue of what's going on with the malware. So now you want to run dynamic analysis. And we're going to use 3 monitoring tools: Process Explorer, Wireshark, and Process Monitor. Process Explorer is a lot of fun. Process Explorer is one of Mark Rusinovich's tools. Mark Rusinovich is an awesome guy. He seems to understand Windows internals better than anybody in the world. And Microsoft finally just bought his company. So he's now in charge of Azure, but he's still writing tons of awesome Windows tools. So Process Explorer is the upgrade of Task Manager to give you far more information about what's going on in your Windows system. And each version of Windows, Microsoft adds more features from Process Explorer into Task Manager. And this helps you answer a lot of questions that I always found pretty mysterious when I first started using Windows. Like, let me just put this to the side so I can blow it up. Okay, here I can zoom in for the people in the room. The recording is not going to zoom in, and I don't have a solution for that. But anyway, remember, there's a bunch of SVC host processes running. Why are there so many of them? What's the point of that? And Process Explorer will actually let you see that. You hover over it. The service host is services running in the background. If you start Windows and don't launch anything and open Task Manager, you'll find it's running like 50 or 80 processes when you're not doing anything. The operating system itself is running a bunch of services, and here they are. This SVC host instance is running those. This is running DHCP client, networking stuff. This one is running group policy. This one is running something called application information and application experience. So in general, there's a fun fact about the processes, which is they are all children of another process. If you know Linux, operating system development, you may remember init. Linux starts with this one process called init. And until a few years ago, every process was a child of init. It would fork init to form another process. It would fork that to find another process. And Windows is similar. So before you log in, while Windows is booting, a bunch of these things run, and they have to run as servers, which is the most powerful account, more powerful than the administrator, because they have to run before anybody logs in to get the machine going. When you log in, you start the process called explorer.exe. So all that junk above this line is Windows, and the stuff I want is this blue stuff, just a few things at the bottom. Explorer is the process that draws the desktop and the start button, and anything you launch is a child of Explorer because you got there by clicking a link on the desktop or in the programs menu or something. So it started VM tools, some kind of Java update nonsense. And then I've got this Labo 301 running and Process Explorer running. The Labo 301 is something I launched earlier while testing this lab this morning. So it's time to mention another fun fact. If some of this malware does some damage to your machine, that's why we're in a virtual machine. This particular one doesn't damage the machine, but you can't run it twice. This is, so if you do run it, and you have to start it again, you have to go to this troubleshooting tab. This happens to a lot of my students. They get confused, they run it, but something's not working. Then they try again, now nothing works. This is quite common for malware. You have to clean it off before it'll run again. So I'm gonna clean it off. To clean it off, you have to kill the VMX3264 process and then delete the VMware VMX3264 file. So I'm gonna put this in the clipboard and just kill that. You won't have to do this on your machine, but I have to do it on mine because I tested this stuff. So I'm gonna kill this. And looks like I don't have the process running, but I'm gonna delete this file anyway. I open a command prompt and delete that file. Okay, so now I'll be able to run it, which is gonna be important in a minute. So Process Explorer is a simple monitoring tool which we're gonna use to monitor what this malware does. There's two other tools we're gonna use, which is Wireshark and Process Monitor. So let me start Wireshark sniffing, which is here. Wireshark is a very common tool. I'm going to sniff the local area connection. The local area connection 9 is a virtual interface and it's not interesting. This just records the traffic. It needs an administrator password from my host on my Mac. And now it's just going to show the network traffic as it goes by. Wireshark, by the way, is not something you can just leave monitoring a network for days and days because it's filling up the RAM. It'll eventually fill up the RAM and make the machine crash. And the same thing is true of Process Monitor, another very valuable tool. A lot of people use Procmon. Process Monitor is here. And so you can specify certain things to ignore and certain things to permit. I'm going to go with whatever I specified before and see what happens. And that's good. See, notice I have 107,000 events. Now 107,200, 300. Process Monitor is monitoring the event log. And the Windows event log is unbelievably busy, thousands of events per second. So this also fills up the RAM and crashes. And if you go through the instructions, it'll show you how to exclude the processes. I'm not going to do it again here because it's kind of annoying, but I'm going to mention how awful this is. This is my introduction to being completely stupid and sloppy, which you have to start that way. So you start your Windows machine and it'll show you thousands of things happening in Process Monitor. So how do you remove it? You just right-click on the name and exclude everything by the name of the process. This is really lame because then malware could totally just use a common name for the process, but you don't worry about that. You say, maybe I got stupid malware that didn't do that. Your first attempt is to just do the simplest, fastest test. And of course, in this case, that's going to work. So you exclude everything that's already there by name until you have an empty board like this. So now all the stuff that's already running in Windows is not showing up. Now I run the file. And the file is lab0103. It's on my desktop. I think I can click Start, Administrator, Desktop. Okay, then this folder, Binary Collection, Chapter 3, or wait, Chapter 1, I think, Labo103, Labo301. Okay, Labo301.exe is here. Okay, I run it. When I run it, things happen. Process Explorer now shows that I'm running Labo103. And Process Monitor shows some processes it picked up. Wireshark shows some traffic it picked up. So let's start with Wireshark. That's probably a familiar, easy tool. Wireshark has a lot of packets. Here's a fun thing I learned from Laura Chappelle's class in the certification, Wireshark 101. You can look for things in Wireshark by strings, which is very handy. So here I got a bunch of traffic. And this particular stuff is going to make traffic with the word malware in it. So I can do frame contains malware. All right. And here, these are the beacons. This is a very common feature of malware. Once you're infected, the malware sends beacons to the command and control server. Hi, I'm a bot. in case you have orders for me, master. And it does this, and the command and control server botnet operator has a console showing how many machines they have, and they order them, you 1,000 machines, go attack this site, you 10,000 machines, start mining cryptocurrency or whatever evil thing I'm doing with my bots. So here it is sending a message every 30 seconds, and you can, in order to send the message, it has to resolve the domain name, and here's the domain name of the command and control center, www.practicalmalwareanalysis.com. We kind of guessed that for one of these samples earlier by looking at strings, but now with dynamic analysis, we have proven that it sends signals to this server. And you can examine the signals. I'm going to stop capturing and follow it. So this packet 107 is a bot phone home packet. So if I quit filtering and look at the packets after it, I will see first it does a DNS resolution to find the domain name, then it does a TCP handshake, SYN, SYNAC, ACK, then it sends some data. The data is interpreted as a bad request. Wireshark makes it very easy to see what it sent. You take any part of the TCP stream, like the SYN here that launched it, you right-click, follow TCP stream. And it throws away all the address data and shows you the layer 7 packets. So it sent 256 random bytes, and then it got a bad request response. This is common. Botnet command and control centers often pretend to be something like a web server or an email server, and they get requests, but they don't actually serve up pages or email. They just want the request, and the response will contain commands to the bot. So this is what it's sending, and these random packets are different each time because this is fake malware. It's not really sending anything. If it was real malware, it would be sending a code number, information about the operating system, and stealing your passwords and whatever else and sending it up off to the command and control center in various packets. And the last thing is Process Explorer. You should, in your labo301.exe, let's take a look at Process Explorer, and you can find the mutant. I mentioned these things before. Here's my Process Explorer. Now, we looked at this just to see the processes, but you can get more information about the process. If I choose this process, I can add a lower pane to Process Explorer, which is View, Show Lower Pane, and there are different views for the lower pane. Now this one, I'm showing dills, but what I want is handles. But I'll just do this for a minute. So here you can see all the libraries that running process is using, which is useful. But the other thing you might want to have more detail is the handles, and that is here. These are the named objects that it refers to. And one of them is a mutant. Mutants are named objects that are shared between processes, and they are used so two processes can send signals from one to the other. Normally, processes are isolated in Windows, where one process has its own memory space. You make a mutant to send a signal to another process, and just like registry keys, mutants are very commonly created by malware because they're a mark that any process can check for to see if this machine is infected. So it creates a mutant named WinVMX32. Which is also like the files it creates. That's the modus operandi of this malware, is to create objects with names like that. And you can also view the objects in Process Monitor. There's a few steps here to get through, but once you filter out all the unnecessary processes, Process Monitor gives you a very nice list of everything the malware did. So here it is, writing a file, and there's the file it wrote. C Windows System 32, VMX32. Then it wrote a registry value in the run key. That's why this is very nice. This is taking a log of everything that happens, and after you filter out everything that is normal, you see just what the malware did step by step. And this proves exactly what it did. So that's the joy of dynamic analysis. And you got that one to run. And I think I'll demonstrate this keylogger because this one is good, clean fun. So keyloggers are going to steal the key presses and save them locally. So we got to open Chapter 3L. We're going to have a few things visible at the same time, Process Explorer and Explorer. So let me stop Process Monitor because like Wireshark, it tends to fill up the RAM. Oh, there, it worked very well. It shows me just those two operations. This is the kind of thing I was talking about at the beginning. I wanted a tool that will show me just the meat, the important stuff, not 10,000 lines of registry entries that don't matter, but exactly what the malware did so I can quickly understand what's going on and figure out what I'm going to do about it. I'm going to get rid of Wireshark because I don't care about network connections now. What I care about is Process Explorer here, and I want to run lab 03 up there. And there's going to be some fun action in Process Explorer. So let me get rid of the lower pane view for now and shrink this down and put it on the bottom of my screen and get to the bottom where so I show the processes that I launch, because I am going to launch something from Explorer. So I don't really care about the stuff above that line. And here I want to launch Labo 303. So you just get this out of the way because you have to see something that only lasts for a few minutes. Okay, there's the file I'm going to run, Labo 303. Take a look at the bottom screen here and watch what happens. Labo 303, there we go. It creates something green, then it turns red, then it's gone. Now what this did, it launched a process that was green. When it turns red, that process is terminated. So this is not what you expect an application to do. You launch Word, it stays open. You launch something, it self-destructs, it closes. And then it created this weird thing down here called SVC host. This object is down here where it does not belong. It belongs up there. It should not be a child of Explorer, and it's even broken out of the child and parent relationship. This is called an orphan process, kind of thing that won't be stopped when you close Explorer and such. So that is a really strong clue that the malware launched something screwy here. And of course, it is screwy. It's a keylogger. It's listening to every key press, not just the key press is going to an active window it controls. So it is kind of crazy, like an orphan Windows service. And now you can see those key presses if you just type those files will show up. We'll do that a little later. But let me show you something else awesome, which is process replacement. In Process Explorer, so we've already figured out that this process is kind of screwy. So let's look at its properties with Process Explorer. In properties, you have a lot of tabs here that let you see everything about this process. I'm just going to adjust my screen to make this as big as possible. Okay, there we go. All right, so what's going on here is you can look at various things about the process, but one thing you can do is look at the strings right here. So here's a bunch of strings, parameter, system critical, RPC, and all that jazz. This is the image on the hard drive of the file that this points to. If I go to memory, I will see the strings in the running image in memory. This is, again, very strange. The memory should be the same as the file on the disk. But this launched through a process called process hollowing, which is awesome. You run a program and you want to run malware. I said you could attach a library, but if that's too much bother or people are catching you with antivirus, you just rip out the guts of the running program, replace it with different guts, and let it keep running. That's what's happened here. After it launched, it replaced the contents of the file, so now it's running something malicious in here that is not equal to what the file name is and the permissions that tied to it. This gave me an awesome idea to deal with my college administration, which is just primarily to prevent all success. And we had a teacher that wanted to teach a class, and I couldn't get it through the administration. I said, well, let's just teach a different class. Tell the students it's a different class, and you can teach whatever you want. This is process hollowing. Anyway, so that is process replacement in action. And we can now test the keylogger. So if I open Notepad and just type in some text, we will see it appear up here. That's why this is good, clean fun. Let me get this extra stuff off my screen. Okay, so I need something to type into, like Notepad. Okay, let's get Notepad down here. Okay, and now make things, okay. So look up here. Now if I type hello from RSA, a file appeared up here called Practical Malware Analysis text document. And if you double click that, it's stealing my key presses. So this is a standard way keyloggers look. They have things you type, they have backspaces. Here's the part I type now. Here's the stuff I typed earlier and the clicks I made while demonstrating the earlier process. That's what keyloggers do. It's running that weird process, grabbing every keystroke before it is redirected to the window it applies to and logging it somewhere. And in this case, of course, it puts it in a nice obvious log file instead of trying to hide it, because this is practice malware, not the real nasty stuff. So that's the game. And I actually modified this file. This was actually pretty easy. I took the binary, I just changed some things so it hides the log somewhere else and you have to find it. Anyway, so the keylogger is fun to watch and fun to play with. And there's a challenge here where you have to find the beacons that a file is sending out. So that's using net wireshark. So give those a try. I'm going to go around and help people a little bit, and then I'll come back and demonstrate more. Let me just see when this ends. When does this event end? 2:30. So we have an hour. All right. So I'll just go around for maybe 10 minutes, and then I'll demonstrate the remaining stuff without a pause to make sure I show it to you all, because a lot of people won't get to do it, but at least you'll want to see it. Check the scoreboard and see how people are doing. Oh yeah, well, we have this person is really zooming ahead. The others are doing just fine. Finished with the first section, on the second section. Good. Okay. Oh, don't keep the USB sticks, please. We're going to try and cut them for future classes. Anyway. You must have your machine working. All right. Anybody else having trouble? Question. Oh, good. There you go. It'll be one of the ones you use here. It's the one that has the hat. Oh. All right, I think I ought to just, all right, I think I ought to just do a couple more demos up here because there's stuff I don't want to miss. All right, so here's, if you want to learn assembly, you should check out Jasmine. This is a German tool that simulates an x86 assembler. And this, if you want to learn assembly, this is the funnest way to do it. Let me make sure I'm not paused. Good, I am not. Okay, good. All right, so you can install it on any machine. It's on those virtual machines, but it's more fun to run on your host. It's just a Java-based tool, so it'll run on any machine with Java. Now I'm not finding it. What is the problem here? Jasmine.jar, I think. Fine. I don't know what happened here. Let me download it. There. All right, fine. I will download it. And there it is. Okay. It's a zip file. I open the zip file. I don't know what happened to my Jasmine, but I don't really care. There's jasmine.jar. Okay. It's a Java archive. And it should, at the blazing speed of Java, pop up and show me something. And then again, maybe it's just going to do nothing. All right, maybe I'll use the one in the virtual machine if this one is just not going to work. Somehow Java has failed on my box. All right, let's go in the virtual machine. There should be one in here. This is the part for the course with Java. Java tends to hose you. Jasmine. Okay, here's jasmine.batch. That should launch it in the virtual machine. Ah, good, okay. And it also gets me to an issue. This is difficult to use in American universities because, as you can see, it is politically incorrect. And I actually made a version that replaced this by a flower. So because American college teachers couldn't use it. But anyway, I'm sure the people that wrote it from Germany would not understand what the problem is. But anyway, after you get past their cheesecake splice page, you get here, which is where you want to be. This simulates an x86 assembler, so you can learn how it works. The assembler has registers, EAX, B, C, D, and E. Here's the extended instruction pointer. Here's the stack pointer and the base pointer. Those are the two registers that point to the current stack frame. Here is where instructions go, and here is memory. And this is a very simple machine like a Commodore VIC-20. It has 4 kilobytes of RAM, and that's it. And you can run things on here. So we can now put in code like move EAX1. And down here at the bottom, it explains to you what the instruction is and how it works. This is the Intel syntax, so it's move destination, comma, source. So everything is backwards just to give you a headache. Move EBX2, move ECX, EAX. You can do stuff like that. Now, none of it has happened yet. I'm just putting in the code, but you can run it here, and you can do it with these buttons. Here's my buttons. All right, this one here will make one step. So it does the first command, which puts a 1 in EAX. This will do the next command that puts a 2 in EABX. Next one is going to take EAX and put it in ECX. And off you go. And so now you can write code and run it here and see what it does. Here's the RAM you can write to. And I have a few projects you can play with Jasmine. You can install some code and run it. There's a little thing you can put in here. By the way, if you want to put code in Jasmine, you can just copy and paste it in like Notepad. It's just plain text. So you can just go here like you would in Notepad, delete the old stuff, paste in the new stuff, and now you've got running code. The extended instruction pointer is still down at the beginning, so I'll reset it. And this code moves some things around. Here it's going to do an indirect move, moving into the address of EAX. So instead of putting EBX in the register EAX, it's going to put it in the memory pointed to by EAX. Right now, EAX is 4, so it's going to put it over there in RAM, and there it is. It put that 6 over here at RAM location 4. So that's how it goes. A normal RAM is at the top. The stack is at the bottom. So if you put things on the stack, let's just do that here. I'm going to push EAX, push EBX, and pop ECX. See how that does? So if I push EAX, that puts EAX on the stack, and you'll find it down here at the other end of memory. And there it is. The first value appears at the bottom of the stack, the 4 way down there. I push another one on the stack, and now when I pop one off the stack, oh, I didn't like it. I spelled it wrong. Good. Turns red and warns you. Okay, then I'm going to pop something into ECX. That puts into ECX the value it took off the stack, and it adjusts these pointers. Now that I have pushed one thing and popped one thing, ESP and EBP are the same, indicating the stack is now empty. And it even has the other thing that we are all, I think, familiar with, which is data remnants. Here, I pushed 4 on the stack, and then I popped it off, but the 4 is still sitting there in RAM. Just like your deleted files are still sitting on your hard drive, leftover data is waiting around, abandoned from previous things, and that's how you use things like use after free vulnerabilities, and many other problems come from this. So this is a good way to learn a little bit of assembler, and that helps you understand the code when you read it. All right, so there's a challenge here where you run some code I give you, and it'll spell out a secret message. There is no console in Jasmine, so all it can do is put bytes in memory and you see the ASCII values, but still you can spell things out sort of. And then there's IDA Pro, which is, I think in the interest of time, I won't do it live. IDA Pro is the first tool I heard about, and it's the reason why I just gave up and said this is impossible. IDA Pro is like Photoshop. When you launch it, you are confronted with 10 toolbars full of baffling stuff, and you just say, oh, I give up. I'm going to go use Microsoft Word or something. And this is where you really face the real complexity of code. And at first, it's hopeless, and this is why I try to help. You need someone to give you a reasonable introduction. What you do is you ignore all of that because that's too annoying, and you look here. This colored bar is a summary of the code, and the blue code is the part you care about. The yellow is something like strings, the green is strings, the yellow is like variables. This is the code that the developer wrote. The rest is library code or something. So this is where you're going to find the good stuff. And you can drag through this to examine the code. That's the first thing. And by the way, another thing that helps when you're a beginner with IDA, when you open a file, it has to process the file, and it takes a while. So at first, this is just gray, and you often have to wait like several minutes for IDA to finish interpreting this code. So that's another clue that could save you some frustration. But anyway, when you're done, it'll try to make it easy by showing you this view where you see blocks of code in a box, and then you can even see a summary of the whole program here, all the boxes and arrows. So it does something, and then it has a jump not 0, so it makes a decision. If something is 0, it'll go one way. If it's not 0, it'll go the other way. That's an if statement, and on you go. So there are some modes you can put here to see more about the assembly code and more about the addresses. And you can now find, for example, you can import one of these malwares and look for all the places where it calls this function, get host by name. You can find where it's doing a DNS resolution. If you say you're interested in finding a command and control server, you might do that. And then you can find all the places. It's used in 10 places. It pops up a box, and you can go look at the code in each of those places. If you just hover over one of them, it'll show you a few lines around it to help guide you. And you can really go to town in this. You can rename variables, rename methods, put tags and notes in your code, and so on. So here I found code that runs this cmd/c, which is the command line to launch a process from the command line. So those are things, you can see this in strings, but in IDA, you find it, and you can actually go to the code that uses it and make sure you understand exactly what it does. So this is where real pros spend all their time. I got a student who actually paid his own money to buy his own license copy of IDA, which is like $5,000. And he spent all day on a very powerful machine doing this, and he discovered a new iPhone jailbreak, first new one in 7 years. Because this is very valuable, but it's very esoteric. And so typically every company needs one IDA expert and one wireshark expert. Wireshark is easier, but in both cases, there's a lot of density to it. You can get into it to really find out what's going on in binaries or on the network. Anyway, there's a very simple intro to IDA there, and a few challenges, and then some script kiddie stuff, advanced dynamic analysis. You can use Ollie. I'm going to do this one, but I think these are the two we're showing you, kernel debugging and SSDT hooking. I can talk about this, and I may be able to demonstrate more some of it. Okay, so if you want to do, this is old-fashioned cheating at Windows games with Ollie debug. This is where it all started for a lot of script kiddie type hackers. So I got a copy of PuTTY, just a common Windows tool, and verify the hash so you got the right version. You can run PuTTY. PuTTY connects to a server, and then it pops up a box saying log in as. Then you can connect to the server, but I don't care about that. I'm gonna Trojan this program. So I want to see how it works. When you start Ollie Debug, it presents the machine language instructions and it tries to make it easy to read. This is a general rule. Whenever you're confronted with a page full of baffling text, look for what you can read. Just think about a child that can't read and they just look at the pictures. That's where you start. So this junk is hard to read. Over here, get version, get module and handle. This stuff is in red and it's over here because they know we can't understand this, so we look at this. This is what you've been seeing in the other tools we've been using, where it just shows you like the name of the module, name of the function you're calling, because this is where you get oriented. So over on the right, you can get a pretty clear idea what this file is doing. Okay, you can run PuTTY in Ollie Debug. That's what debuggers are for. You run it, it runs in the debugger, so it can break and change the execution. So when you launch it, in debug run, it then opens up the window, invites you to log in. When you put in the name of a server and press enter, it shows you to log in as, and all I want to do is find the code that prints this message, log in as. So to find it, I can restart the thing, and I can look for all text strings. If you right click and look for all referenced text strings, this is like strings. Like I was talking about in IDA, you can look for strings in the code, but you're in a debugger, so you can learn more about it. So you can search for text, look for the text, log in as, and you will find a few examples of it. Here's one at address 46, 7C, 7C. And if you go look there, you can put breakpoints at those spots. F2 will put a breakpoint on it, so you can run, it'll stop when it hits there, and you can then run it and see which one is actually used, and learn which one of those actually prints out the message. And that's this 467C, 7C. So let me just do that one live. That should be reasonable. I should have the PuTTY in the downloads folder. Let me take a look. And I do. I'm just going to make a copy of it. There. So I got a backup in case I foul it up. So let me start up Ollie. Okay, there's Ollie Debug. Okay. And by the way, like Photoshop, it has a bunch of windows and they're too confusing and irritating. So the one you want to see is the CPU window. And I'm going to open my file, which is going to be that PuTTY file. So it is administrator downloads, PuTTY. I think I'll open the copy. All right. So now, the windows here, the one on the top left shows you the executable code. This is a hex dump pane, just like you dump memory, like you might in wireshark. On the right, you see the stack. Those are objects on the stack in order. And on the top right, you see the registers, the same things we saw in Jasmine, EAX, EBX. Here's the stack pointer and the base pointer. Here's the instruction pointer showing I'm at the entry point of PuTTY. And by the way, one thing to know about debuggers is when you load something in a debugger, it loads the file and stops. It is not running. If you try to connect to it, it's not there. That is by design because they think you might want to look at it and put in breakpoints or something before you run it. So if you want to actually use it, the first place you look is down in the corner where it says paused. So you know it's not actually running yet. So I'm going to run it. Well, I'm just going to do that step. Let's find the all referenced text strings. All referenced text strings, trying to zoom in and make it as big as possible. Okay. And now I look for login as. And one thing that often frustrates my students is they're actually in the wrong module when they start looking for things, and that doesn't work, of course. Let me see if I can find my scroll bar and get to the top. There we go. Because it searches down. So now I can right click, search for text, login as. Okay. And let me try and get this to fit on the screen better. There we are. So I should have a login as somewhere highlighted. There it is. So there's a login as. All right. And there, that's what I wanted to get here. And I want the next one. I just happen to know I'm not going to bother to get them both. That's still that one. C6, I think this is the one I want. So I'm going to put a breakpoint here with the F2 key. It turns red, meaning it'll stop when it hits that point. So let's see if I hit the right point. I'm going to restart my program with debug restart. And now it's ready to run. It's paused again. You can see it in the corner. But if I run it here, it runs and launches the program. Now I put in something to connect to. And I connect. And now it draws the black box, but it does not print the login as message because it hit the breakpoint. And so I know that it stopped at the breakpoint, and I found the case where it prints the login as message. So now I want to alter it. So I'm going to go remove the breakpoint, and now I'm going to go to the code that uses it, 41C6BE. There are various ways to get there, but wait, I got a network error here, so it didn't get as far as I wanted it to. But anyway, I'm not going to worry about that. Let me get to 46. I can go to an address expression, and the address I want is this one. I'm going to copy and paste it so it is not as frustrating to deal with. There. I can go to that address there. And now you see Ollie Debug helpfully shows me this is going to take the string ASCII login as, and it's going to load it as arguments to a function and call that function, which is going to print it on the screen. So if I wanted to alter this message, this address right here, I can right click and I can follow in dump. And it's irritating me down here by not going quite where I wanted to. But anyway, here's where it is, 467C7C. Let me try that again. I should have been able to do a little better there. Follow in dump, immediate constant. There we are. That's what I wanted, 467C7C. That's where strings are stored, and it stored the message login as. So if I change this, that is the address right there. I can press space, and it will let me assemble the code and edit the code. So I'm just going to add one to the address. So it points to 467C7D and assemble that. And now it turns red to show it's changed and cancel it. I've now modified the code. Now I have to save the modified code, and that is a little bit annoying. You right-click, copy to executable, all modifications. Took me a long time to learn this. For some reason, it's hard to do. Right-click, copy to executable, all modifications, copy all, and now right-click, save file, and now I can call it putty2. There. I'm going to call it puttymod. All right. Now I've modified putty. I can leave this and run it from my downloads folder. And there's puttymod. And when I run puttymod, if I connect to a server and open it, I think I've lost my networking somehow. Apparently not. Somehow, so I can't, somehow I've fallen into a sandbox. That's where I should be, right? Yeah. Yeah, somehow I've lost my networking. All right, I'm not going to worry about doing it live because we're in the last half hour here and there's something else I want to show you. Anyway, you'll get this message login as, and then if you follow here, you can actually add Trojan code, make malware with Metasploit, add it to the executable, and now have it open a listening shell and give people remote control of your machine. It's easy enough to do. It's easy to do in Windows, and it's a good thing to learn. And this is how people cheat at games, give themselves more points and more weapons and stuff, is how it started. But the last thing I want to show you is kernel debugging, because that is good, clean fun. So here's kernel debugging. What we've been doing, everything so far we have done in user mode. Anything you launch from the desktop or the start menu is in what's called user land, ring 3. These are unimportant, relatively harmless instructions. The really important instructions that directly connect the hardware are beyond your authorization. If you're using Windows, only the kernel can do that. So if you want to send something out the network card, you cannot do that. All you can do is ask the Windows API to please send it out the network card on my behalf. Only the kernel can directly touch the hardware. And if you want to make a rootkit that will live on the machine forever and be very hard to remove, you want to put it in the kernel, and people do. So if you want to debug the kernel and put in breakpoints and stop it and pause it the way we were doing with Ollie, you need 2 machines. Because you're going to stop the kernel in one machine, everything's going to stop. So you have to have 2 machines with a serial cable connecting them, if you can even find any hardware that has serial cables anymore. And that's the way Microsoft likes you to do it. But Mark Russinovich, the hero of the world, wrote this thing called livekd. And what this does is it makes a crash dump, which copies the RAM in the kernel, and then it lets you analyze the crash dump in the debugger. So you can't run it and put in breakpoints, but you can examine the kernel of Windows with a single machine, which is much, much more convenient. So this glorious thing called livekd will let you run WinNG, which is Microsoft's debugger, and WinNG lets you debug the kernel. And the thing about this explains how malware authors and everybody else learns how to use undocumented Windows functions. You can very easily look at the guts of Windows and understand it here without it being too complicated. If you execute the command bang process, it will show you the processes. It'll show you first the WinDebug process itself. You can view them with Task Manager, and you'll see the PID, and you'll also see them here. And then you can get a whole list of them with processes 00. This will give you a command line version of Task Manager, show you all the processes. There's online help with .help in the program, which will teach you how to use all these commands. In this really old help menu, you may remember from like Windows 95, using that help viewer, chum files. And you can list, LM lists the modules that are loaded. And in a Windows machine, you've got the kernel itself and many other things running. Here's WinDebug, and there are other modules. NT is the kernel. It's always loaded in a running Windows machine. Can't even boot up without running NT. So you can now view the memory in NT. You can see the code that's running Windows. And you notice this is an executable file like the ones we've been playing with. Starts with the MG file header. This is NT itself, the kernel, called ntos kernel.exe, and NT in this tool. So you can examine this file, and you will find all the functions in the kernel with their names. And some of them are somewhat readable, like pop validate existing hibernate file that would have something to do with hibernation. And some of them are pretty baffling, like high quantum end. And some of them are documented in Windows documents, and a lot of them are not. But you can just figure them out here. You can unassemble the function and get right down to the assembly code in it to see what's happening. And you can also examine data structures. If you go to a driver object, you can just see the kernel's driver objects, and you can see what's in here. And here's where you have driver name and unload major function. So you can find how drivers are built and how they work. And this is what you do. So you can find a couple function names and disassemble beep. Beep is a function in Windows. So you go beep when you press Control G. You may have noticed a couple of weeks ago, the beep function in Linux had a privilege escalation vulnerability. Windows, as far as I know, doesn't have that one, but it has the beep function, and it's so simple you can pretty easily examine how beep works. In both cases, it's only about 20 lines of assembly code. How hard would it have to be? So you can do the basics of kernel debugging, and then you can see the joy of SSDT hooking, which is the last thing I'm going to point to. This is a horrible technique that Microsoft hates of adding functions to the kernel. You may remember when Vista came out, Microsoft said, we are going to implement signature checking at boot up in Windows Vista, so that every time it boots, it will load the kernel, compare that hash to a signature, and refuse to boot if it has been altered, and that will be the end of all rootkits. No more persistent malware in Windows. And they didn't do it because Norton and McAfee sued Microsoft and said, if you do that, we'll go out of business because we have to be able to mess with the kernel. And Microsoft said, well, we don't know what the right hash is if anybody else is messing with the kernel. The whole point was to lock everybody else out of the kernel, but Microsoft can't do that because they're effectively a monopoly. Apple can do anything they want because they say, if you don't like it, go buy a PC. But the PC had their antitrust lawsuit. They're pretty much own too much of the market to lock other people out. So they did not do that. Although now they're adding it supposedly to the very latest versions on some hardware. But anyway, the SSDT is the system service descriptor table. And we use this and the Linux analog called the global offset table a lot when making malware that takes over machines. The SSDT is an offset. And this has been around forever. I remember doing this in a Commodore 64. When you would jump to kernel routines, you don't jump directly to the kernel routine. You jump to a lookup table, which then goes to the kernel routine. And if you write a program with functions that calls library functions, it doesn't jump directly to the library function. It jumps to a local lookup table, which goes to the function. And this is absolutely necessary for a simple reason. Suppose I'm running some program like PuTTY, and then I want to update PuTTY to remove bugs or something. I want to be able to change the code in PuTTY and continue to run it on an old OS. So if I have to move a function, like there's enough room and I have to make it bigger, I have to have a lookup table that will redirect the code to go find the new function. Now suppose I want to put on Microsoft Windows updates and continue to run my old compiled code on the new updated version. And Microsoft wants to update some routine and make it bigger, and it won't fit in the existing memory. They need to move it, and they need to upload the SSDT. They update the SSDT with the new address, so all my code that uses a kernel routine goes to the SSDT entry, which Microsoft updates as part of the update, so it finds the new method. So this is necessary for the flexibility of being able to update the OS and the code separately and have it keep working. But what it means is, if I'm a bad guy and I want to do something like make a keylogger, all I have to do is change the SSDT. So every time it calls a Windows kernel function that reads the keyboard, it goes to my poison code instead and makes an extra copy of it before passing it on. So hooking the SSDT is an awesome way to make a rootkit. And so you can examine the SSDT with this command DDS chi service table in the debugger, and you will see the SSDT, which is just a list of pointers to all these things. Here's where the pointer is. Notice it's just counting by 4 bytes, 70, 74, 78, 7C. Then these are the 4 bytes in there. This points to where that NT function is, this points to that NT function, and so on. All of them will have the same general address because the NT kernel is not that big. It's loaded in my machine at address 81A to 81C, so all these are in a small range. Okay, so you can put those in a log file with a couple of commands so you can look at it. Now you can install something to see it happen. There's somebody wrote a demonstration of this called SSDT hook. It doesn't do anything, but it changes the SSDT. Now when you examine it again, you'll see there's a funny number here, 94 instead of 81. That is not a valid Microsoft pointer. And it'll warn you here, I was not able to figure out the name of that object. It wasn't in the table of Microsoft object names that I expected to find it in. So it's pretty glaringly obvious in the debugger when somebody has messed with the SSDT. And anyway, so you do that. One thing I thought was awesome, I needed to find some malware that hooked the SSDT. And I couldn't find any. So I found out that security software used to do this. Zone Alarm, for example, a firewall, does this. All security software did this until around 2010 or 2012, when Microsoft finally got really sore about this and said, look, everybody quit messing with the kernel. What's wrong with you people anyway? Remember when Windows XP started having this box that popped up saying, you had a problem, please tell Microsoft about this. They collected those crash reports and they said 75% of the blue screens of death are from other people's code hooking in the kernel. You idiots write sleazy drivers. You take your MS-DOS driver, you change the header to say it'll work on XP, you sell your NIC for $10. A million people use it, they get the blue screen of death, and then they call Microsoft. Your operating system sucks. And they're like, dude, it's not our operating system. It's that $10 driver you got from China. And so everybody did this, and all the security people did it too. So if you install Zone Alarm, you'll find a whole bunch of those hooks in there. That's how it works. Because the antivirus has the same issue. You double click on the file on the desktop, Explorer tries to launch it. And Norton comes in and says, wait, before you launch that file, I have to scan it. So it has to hook the SSDT to do that or do something equivalent. And that's why their point is you can't lock us out of the kernel or our whole business model will collapse. But Microsoft has their recommended ways to do this, which people are switching to, other than just blatantly hooking the SSDT. So I think that's the last one I wanted to show you. I've got more of these. I'm doing them at various conventions. I'll be doing all of these at Circle City Con in Indiana and so on. And if you want to see any of this, I got whole classes here that I teach at City College. Now it's free. I have online, I have videos for the lectures and a lot of homework and online quizzes and stuff. But anyway, so there's more of this stuff to do. These are the ones I've got all gamified like this, which I think is the best way to do it, at least for conferences, probably for students too. So I think I'll just go around and help people. Got any questions? Yeah.
So data entry in the SSDT table, you got to work with Microsoft.
No, you can just modify an existing machine with administrative privileges and just write to the SSDT. It can't stop you, but Microsoft doesn't support it, and they don't promise not to kill it with updates and stuff. But it turns out that an enormous amount of software uses non-supported, non-recommended procedures. There are these undocumented things, and they just sort of move around like lore until a lot of developers know it. Often the easiest way to get a job done is to do something horrible and sleazy. Like, in fact, let me just show you a very simple demonstration here, one you've probably all seen. In my exploit development class, this is the first thing you do is the ping form. You've probably seen this. So your router has a page that says test my internet connection. So you put in an IP address or a domain name or something like 127.0.0.1. And this is written in PHP, but the developer was too lazy to figure out how to send a ping from PHP. So what they did was create a command line of bash that is ping followed by the IP address and executed in bash. And you recognize the standard response to a ping code here. This is what developers do when they just take the easiest path to get the job done without worrying about little details. And the problem is I've now created a line of code which is parsed by bash. It includes data that came from me. So if I put in 127.0.0.1 semicolon ls, it does the ping and then it does an ls. And I can do any amount of commands I want. I can execute code on. So this is a code injection vulnerability. And what's awesome is this is what just happened to Drupal last week. I couldn't believe it. I give this to students. I have a box running ImageMagick from 2014 because ImageMagick was a Linux processing library with this kind of vulnerability. I love these because they're so easy, beginners can do them. And the Drupal one is like that. Let me point it out, it's awesome. Most of the exploits you see are pages of binary complicated code, and they're not these ones. Drupal, if I find, that's the Metasploit code, but if I find the original proof of concept, which is here, this is the Drupal exploit. Yep, the exploit.python. Oh, it's a whole Python file. Yeah, it's a whole Python file. It has one line. There it is. Let me just copy it and put it in a text editor so I can wrap. This is the Drupal exploit that is destroying the world right now. Don't save that, but give me a new one and paste it in. Okay, this is my Drupal exploit. It calls this line of code creating a payload for a request. A single HTTP request is the exploit. And the request is going to some kind of register for mail function in Drupal, and it has this field called mail markup. And in that field, you put echo a smiley face to hello.txt. You just put bash commands right there. So it is so simple. This is why Drupal freaked out. They said, next week, patch your stuff. We're delaying the patch for a week. Oh my God, as soon as people see how to do this, you're all dead meat. Yeah, 20 minutes ago. Okay, anyway, so these ones are fun when they come by for beginners. You can hack a machine with very little knowledge. And the point is here you inject bash command line code, then you move to other ones where you're injecting other things, and eventually you get to where you're injecting binary code. And that's what we do in the exploit development process. But anyway, that's all I wanted to show you about this malware analysis. So I think I'm going to stop talking unless you got questions. Yeah, you need help over there? Okay, let me go over there and help people. I'm going to stop the recording, and I'll just help people until we run out of time here.